In theory, what you should already have written down is what's written down up on the screen. You got a little bit longer than I did to write it out, and that should be roughly your pace. Get down what K is. Note that I'm putting in products over reactants. I think that becomes relevant when we start moving into Le Chatelier's stuff. Okay, so I want to simplify my image when I go through and deal with it. I plug in my numbers. Note the color change. Why a color change? That color change is because we're testing to see if we are at equilibrium. We're not technically solving K at this point. We're solving for some unknown, technically. When we go through and run that calculation, I believe we get something like 600, okay? Which tells us what we're solving for. What did we solve for? Q. It's not K because what does K equal? 21. Okay. What does it mean if we have a K or a Q that is significantly larger than the K? Careful. Our products are in a higher concentration than they should be. Okay, so it's not product favored. If we're going to bring in the term of favoring, we're not going to say product favored, we'd say reactant favored. Okay? Because we've exceeded beyond where we're supposed to be with the concentrations of products, which means the reverse reaction has to happen. Okay? So the product concentration was too large, which is why I'm getting a Q that is too large. Kind of, sort of? At least for you. Okay? This is where Dr. Schneblin likes to bring in the number line, which I had never seen before, but seems to make a lot of sense as well. You're looking at that number line of effectively 100% reactants versus 100% products. What would your K be if you were 100% reactants? Okay. This is where you get 1 or a number over 0. Okay. That's going to be a really strange number. Okay, it's never products over reactants. If you're 100% reactants, you've got a really large concentration of reactants. Okay, so you're approaching 0. What if we had a K where it was all products? What's that? That's approaching infinity. Okay? So we're looking at that system. Okay, so we're just trying to slide around that number line. So we're looking at a K that is really, really, really big, or a K that is very, very, very small. Okay? We would put our Q on the number line, we'd put our K on the number line and see how we would have to shift. If we're at 600 to get to K, what has to happen? I have to make more reactants. I'm sliding towards the reactant side of this line. Kind of make sense? Whoa, what just happened? So that sets us up with this kind of summary. Okay, again, if you don't want to manipulate the number line or think as much as might be useful to go through and deal with your Q's and K's, you can go through and in these colored boxes, your pink and orange boxes, those would be things that would be useful to include on your cheat sheet for the quiz on Wednesday. Okay. Really just kind of summarizing all of those major points. Kind of make sense? Okay. So what happens if the reaction is at equilibrium and we change the concentrations? Okay, so what happens to the concentration of carbon monoxide if the reaction is initially at equilibrium and we add more carbon dioxide? Write the equilibrium constant expression and use it to explain what happens. Again, a blue box. Let's try this time with a few more words from your mouths at your tables. So what happens? One thing I'll throw out there that a couple people noticed and stumbled across. We've got CO and CO2. You got to make sure you keep clear which one's which. Okay. One thing I would go through and do potentially is I don't want to look at CO necessarily. I want to look at
CO2? No?
what would happen to the concentration of products. If we added more reactants. Okay, so if I have more, I totally wrote my K expression backwards. Sorry. Oh, I did it all the way back. Damn. Okay, let's just leave it at that. That way we can fix it. Okay, so in the Q, what happened? I added more reactants. So my reactants gets larger. Products. What is that going to make my Q relative to my K? So what has to happen? What has to happen to re-achieve that equilibrium? Okay, to shift that direction, I would have to increase products. What does the question ask about? Well, what would happen to the concentration of products? So what's going to happen to the concentration of CO? That's going to have to increase so that I can get towards my K. Can you see that? What's going to happen to the concentration of my reactants? Say again? The concentration of reactants are going to have to decrease. So those two concepts are tied with each other. Because you can't increase the products unless they come from somewhere, and where they're coming from is our reactants. Kind of, sort of?
Yeah.
Questions?
Just so I'm clear, so the question specifically states what happens initially at equilibrium. So is it in the wording?
So let me clear all that away. So what would happen to the concentration of CO if the reaction is initially at equilibrium? So we're saying we're starting at equilibrium. Here's our initial state. What happens to it when we mess it up?
So obviously reactants go up. That means probably that initially it's Is initially going to decrease? Is it going to decrease because of the imbalance now?
Yes.
So just on the surface, one went up, the other one naturally goes down? Or it's just a smaller Q value now?
So what we have is a balance of reactants and products. So we're now at equilibrium. Okay? What this is saying is what happens to the concentration that's at this balance if I add more CO2. Where is CO2? Since I already screwed it up. It's on the reactant. So now I put more reactant over here. That's my change. Okay? What's going to happen to the concentration of... God, I freaking did it again. No, I didn't. We added more CO2. I did that right.
Yeah.
I'm getting confused with the CO and the CO2. Okay? So if we were looking at this state, as soon as we've done this, we're now out of balance. To re-get to balance, what has to happen? I have to take a chunk of those reactants and turn them into products. So what's happening? My product concentration must go up to re-achieve that balance. Kind of, sort of?
Yeah.
Okay. So that seesaw, I think, can help a lot in trying to figure out that balance. We good?
Yeah.
This observation, I don't know if it was necessarily first made, but it was addressed or given credit to Le Chatelier, and it's called Le Chatelier's principle. I believe we talked about if you see your friend balancing on what foot, what do? You go ahead and you push him. right? And they're going to wobble back and forth. That's what our chemical reaction is doing. It has achieved its balance. It is now balanced, and then we come through and tweak it, right? Out of stress. That stress is going to cause a wobble as it maintains equilibrium. Right? So what are the things that would affect our equilibrium? Oh wait, who's coming through the door? We're supposed to turn and look, but okay. What is our equilibrium expression? K equals? Products over reactants. Awesome. And everybody loves it when I say this. Do better. Concentration of the products over the concentration of the reactants. And of course, we can follow that with do better. A less vague response might be, what is concentration? That one wasn't supposed to be a hard question. What's concentration? I like molarity better. Okay. Do better. There we go. Moles over liters. Why does this become important? What we're concerned about is at equilibrium. Well, what things contribute to the equilibrium? Concentration contributes. Okay, but what is concentration? Concentration is the number of particles, moles, and it's also the volume, okay, or related to the volume. Inversely related because our volume is in the denominator, which means when we're trying to go through and figure out what things are going to be stressors on the system, what we want to consider is what things affect our K. So right out of the K expression, right, the number of particles, concentration, volume, all of those are now explicit things within the K expression. When we start tweaking those, that's going to change the numerator or the denominator, and that's going to change our K value. So what we want to do is consider those changes in our K expressions, okay, as stressors. Okay? But if I bring in the number of moles and volume, does that bring in another potential thing I could contribute? Whoops. I wanted volume. What is N? Moles. What is V? That's a fair answer to that. I was looking for liters. Okay. And so right out of PV equals nRT, we have concentration directly related to pressure, which means changing the pressure will also change our equilibrium constant. So that can be another stressor to the system. Kind of, sort of. The last one I would argue is a little bit hidden, okay, but it is kind of embedded in there. PV equals nRT helps to bring it in. Temperature. Temperature does affect your equilibrium constant. Okay? It affects your equilibrium constant by going back through all the delta G thermodynamic nonsense. Okay? So changing temperature can also act as a stressor on your individual system.
Are we going to see Q on the quiz on Wednesday?
Yep. What is Q? It's the same thing as K. Okay? It's an interpretation of K. That's it. Okay? How do we get to that point? So if we look at a new system here, predict what would happen to the concentration of CO2 and CH4 if the reaction was initially at equilibrium and the H2 was removed. Okay? So again, how I would simplify, CO2 and CH4. So I would go back to my expression. My CO2 and CH4 are reactants. And here I want to know what happens to them. So I'll put a question mark on that. What's going to happen to my reactants? Okay. What's going to happen to my reactants if what? If the product is removed. How does that change my system? Okay. If I decrease the product concentration, what's going to have to happen?
Reactants increase.
If I come in and I cut a section of that product out, what happens?
Reactants comes out.
That change now results in your reactants being too large in comparison to your products, right?
Yeah.
So what has to happen to account for that? Let's put more reactants over here. That didn't work, right? If we put more reactants, it stays anchored. What do I need to do? I need to take a section of my reactants out and turn that into products. That now reattains my equilibrium. So what happens to my reactant concentration? What did I do?
You decrease it. I see.
I decreased my reactants. Kind of, sort of?
Yeah.
Do you like the fulcrum seesaw thing?
Yeah.
Okay. Do you want to look at the number line also?
No, I like it.
Yeah? Okay. Let's double back to the number line for those that care. For those of you that don't want to look at the number line, then close your ears. RK expression is products over reactants. If I'm going to go through and solve Q, my product concentration is removed, which means I have small products and I have large reactants. What's going to be the size of my Q value? So we could start to manipulate our numbers, okay? I would think just relative to K. What happens? There's my Q. What has to happen to move from Q to K? Increase in products. What did we say needed to happen? On the fulcrum seesaw thing? An increase in products. You're getting the exact same result in both cases. It's coming down to which system you're better able to manipulate and understand. Kind of, sort of? Okay. Yes.
So, molecules from the reactants are being transferred to the products?
Yes. So what's happening is it's at equilibrium, closed system. We effectively reach in, we remove hydrogen, and then we close the box back up and say, what are you going to do? What are you going to do about it? And what it's going to do about it in this particular case, because I've removed the product particles, the reaction's going to have to shift to increase the product concentration to make up for that loss of products. Kind of makes sense? Where's that increase in product concentration coming from? How do I get more products? It's a closed system. It has to come from the reactants. So we're recognizing that this system is dynamic. You have a mixture of reactants and products constantly swirling around. Okay? We are somewhat magically coming in and just removing those products. Okay? It's not magical. There are systems that allow us to go through and remove particular molecules. Okay? But it depends on the reaction, depends on the systems. Here, all we're trying to say is, do you understand what would happen if we did this? Kind of, sort of? Okay. So predict what would happen to the concentrations of NO2 and N2O4 if the reaction was initially at equilibrium and we decreased the volume. Okay? When we're decreasing the volume, what's that going to do to the pressure? The pressure is going to have to increase. Why do we know that? Okay. If I make that denominator a smaller number, my P has to get larger. Okay. There are some extra kind of statements within this. She's mentioning that pressure increases and the temperature remains constant. Why does the temperature need to remain constant? Because all hell breaks loose and you enter now into thermodynamics for real in a more advanced chemistry class. Okay. So those other systems now need to just remain constant. That makes your life simpler when you go through and run calculations. So think about what happens to the concentrations and the reaction rates. Same deal, talk at your tables, see what you come up with. What do you guys think?
Concentration increases.
Concentration increases, okay. What is that going to do to, well, are they going to equally increase concentration? Said another way, if they're equally increasing concentration, did we create a stress to the system?
How are they increasing concentration?
Okay, so there's a different question. That goes back to our PV equals nRT expression. If we decrease the volume, our pressure has to increase, and if our pressure is going to increase, that's effectively our concentration. Okay, that's an easiest place, or the easiest place to see it. You could also go back and say we're looking at molarity, which is moles over liters, and if we make that liters a smaller number, your overall concentration is going to go back up. Okay, both of those are going to lead to the same system. It's just depending on, are you looking at it as a gas or are you looking at it as concentrations? So we decreased the volume and it wasn't a big deal. We're still at equilibrium. Joe, you seem to disagree. Why do you disagree?
Because when you change the volume or pressure, the equilibrium constant also changes.
It doesn't have to. The only reason it has to is because the concentrations of products and reactants are changing unequally. Did anybody write down the K expression? Does silence mean no? No, you didn't? Okay. If we take a look at the K expression, products N2O4 over NO2. NO2 squared. Okay. Since we're decreasing the volume, both our concentrations are going to increase, right? Okay. And they should increase with the exact same magnitude because there is no way to differentiate those. So let's just say it doubled. So we'll call it a new system. Okay, post change. Because there was an argument that this isn't Q, so I'll put Q or K. And if our concentration of our N2O4 doubled, what happens? Well, we'd have a 2. Okay? And in this case, what we were doing is just ballparking and just saying we started at 1. And 1 squared, right? And if it doubled, what happens to the concentration of NO2? It doubles also, right? But it is squared. Which means our Q, our post change, is now actually smaller than our K. So what does that mean? Changing the volume here did knock us out of equilibrium. Why? There was one small piece that caused us to get knocked out of equilibrium.
Is it because the NO2 is squared?
It's because the NO2 is squared. Okay? Because it is squared, it is taking up more of that volume, which means when we change that volume, what's going to end up happening? That particle is going to have a larger effect than the reactant or than the product particle, which means our K value is going to skew out of balance, and we're now going to be at a Q. That Q value is smaller than K, which means we're down here. What has to happen? We need to increase our products. Or decrease, or technically and decrease our reactants. Is that one hard to see? Okay. Remember when we talked about entropy? Is this an increase or a decrease in entropy for this reaction? We start with 2 particles, we end with 1, which means that's a decrease in entropy. So you're looking at the number of particles. As your number of particles go down, we're seeing a decrease in the amount of entropy. Okay. Why is this going to be useful for us? If we're decreasing the volume, we have smaller space for our particles to occupy. Okay. Which of our particles is going to feel that smaller space more? The reactants with 2 particles or the products with 1 particle? The reactants with 2 particles will feel that decrease more, which means it's not going to like that, and it's going to want to try and adjust back to its natural state. It's more open balance. To do that, it's going to convert those reactants across to products. So our K does not end up changing, but what the change does is it takes us out of equilibrium. So we can use the same kind of analysis that we would have used in entropy, trying to look at the number of particles, okay? Because those number of particles are going to be directly related to our concentration via moles over volume. The number of particles is our moles. Kind of, sort of? Okay, which then takes us to our big kind of summary. Volume, pressure, all affect equilibrium. They're through PV equals nRT. Okay? Each of these changes does not change our K value, but it could change the balance of reactants and products and put us in a Q situation instead of a K. And if we're in Q, the reaction has to adjust to reobtain that K. Okay? So what we're looking through is, again, those initial relationships that we've already defined, and now we're saying, how do we balance out to achieve those things? Kind of, sort of? Okay. So how does adding a catalyst affect the rate of the reaction? How do you think it would affect the equilibrium constant? This is, again, a blue box. I'll give you a minute. I'm hearing lots of good words, okay, particularly about what catalysts do. What do catalysts do?
Speed up the reaction.
They speed up the reaction. Cool. How? Say again? Okay. So if I add a catalyst, all that's changed is the activation energy is now lowered. Should this affect K? If I look at K rate constant forward, shouldn't my rate constant forward be significantly larger if I'm catalyzed? Yeah? So why is it not affecting K?
Well, that K is not equilibrium K.
The capital K up here is rate K, and if I change KF, capital K is going to change. what I've intentionally left out is what else changes.
Backwards.
The backwards rate constant also changes. If we look at the forward versus the reverse, wow, that's an E, reverse, we're also seeing a change in that activation energy. That change is consistent for both of those directions, which ultimately means no change in the overall K. Kind of makes sense? All right. Let's lean into it a little bit more. When did we talk about equilibrium K? Well, this entire unit, right? We didn't talk about equilibrium K in the first unit, though, right? What was the first unit about? Kinetics. And if we look at my diagram, where's kinetics? It's all really dealing with this. This is all my kinetics. And when we moved to the second unit, we now started talking about thermodynamics. And thermodynamics in this diagram is all down here. So if I'm looking at a catalyst, the catalyst is changing the kinetic part. It has no direct effect on the relationship between the reactant and product energies because the reactant and product energies are maintained. They have the exact same energies. K is heavily dependent on those systems. We're not going to see an overall change. Okay. This is why that very first lecture, when we broke down an energy diagram and looked at the differential between kinetics and thermodynamics, can come in handy because K is a thermodynamic factor that can be extrapolated from kinetics, but ultimately is a thermodynamic factor. Kind of, sort of? Okay. So, conditions that affect our equilibrium: concentration, volume, pressure, and temperature. Why does temperature affect it? So we could play with PV equals nRT, which I admittedly have not actually done to see that it matches, but we have a different way to get to that temperature effect. It should match that. Say again?
Is it because if it's like endothermic or anything like that? Because if temperature increases, wouldn't the reaction rate also decrease? Or no?
It does change your speed of collisions and all that. Where would we see anything about temperature affecting equilibrium?
Oh, no, I'll take a look.
You remember the quadrants?
Oh, this is.
Yeah, your quadrants are directly related back to your equilibrium constant. So if you're looking at an exothermic reaction, increasing the temperature causes your K to decrease. Right? An endothermic reaction causes your K to increase. We have those pieces of information straight out of our table. We went through and did a whole bunch of solves with that. Okay, but what I want to do real quickly here is do a slightly different system. If I'm endothermic, where would I put my heat term in a chemical reaction?
The beginning.
And if I now look at a stressor, like changing the temperature, if I change the temperature, if I increase the temperature, what does that mean I'm putting into the system? More heat. What does our reaction do? Heat, in this case, is a reactant. What does our reaction do when we put in more reactants? Think Le Chatelier. If I put in more reactants, what happens? I make more products. I shift away from that stressor. So the changing the temperature can be used directly as a reactant if you're considering endothermic versus exothermic and that heat term in your chemical expression. If you don't like that, that's fine, right? But that heat term being added to your chemical reaction can allow you to predict a lot of those changes when you're looking at the effects on your reaction. Whoops, now that's upside down. And scroll so that you don't have to see. And this one confuses me. Because there's this question and then there's this question. They're the same, are they not? Yeah. What's the only difference you see? What's that? I mean, technically there's a couple differences. Oh, lost my cursor. We're seeing the delta H and the delta S added in here. I'm not sure why the delta H and the delta S were added into this slide or why this slide was provided. Okay. It could just be a system to go through and now mathematically quantify those individual changes by solving for delta G, then solving for K, and then doing all of that fun stuff. Okay. I'm not sure I see the value in going through that. And by I'm not sure, I'm sure I don't see the value in going through that. Okay. Which then takes us to this last question. This is the last one I really want to get through. If you start with 1 molar A and 0 molar A2, estimate how much A2 you would have at equilibrium. Okay. It is another blue box, so spend some time. Write it out. If we were to go through and put in some other values, I think she's been using green for the KEQ. Okay, it's at 23.5, so it's more on the product side than the reactant. Our Q is coming in somewhere lower than that. So somehow or another, we have to increase the concentration of the products. But in this scenario, we're not being asked just does it increase or decrease. We want an absolute, okay? Or not even an absolute, we want a ballpark estimate on this. Okay? Should it be over 1? Okay, why should it not go over 1? I can't have more than I started with, which is why that answer isn't even up there. Okay, so that was a valid explanation. It can't be more than 1 because that wasn't one of my answer choices. Okay, but it's not an answer choice because I can't have more than what I started with. Okay, what is it going to mean if I hit that 0.5? They're in the middle. Okay, where's my K value? I need to have more products than I have reactants. Okay? The question is going to become how much more products, and that gets a little bit dodgier to go through and analyze, but what you're trying to do is predict that individual balance. One of the things that's going to become a little bit trickier to deal with is that it's products over reactants, but our reactants are squared. So we do have to take that into consideration between that. If we did 0.5 as our concentration of our products and 0.5 as our concentration of reactants and squared that, what are we going to get? Two. Okay, if you're wondering about that, 0.5 cancels with the square, you get 1 over a half, which is going to get you at 2, which still means we're still not there. So you would still need to push on this to kind of get this to go across. Okay? So what we're trying to do, yeah, that's wrong too, is figure out how to make that imbalance. And so how are you going to push that further? Increase the products just a little bit more so that your reactants can concentration can go down. Which sets us up where? C. Kind of makes sense? Did I miss an extra step? Oh. I'm gonna stew on that a hot second. If we continue to go through the slides, what we've got are now putting it all together. So these are now multiple ways that we can try to assemble all of the stuff that we've talked about. We can calculate delta H, delta S, delta G. Okay, so these are now multiple practice problems to go through now. This is not new content. It's just more stuff that you can go through and interpret. So the question becomes, what do you want to look at? Do you want to go through and do these practice problems on your own? Okay, or do you want to look at the practice quiz, right? Or what? That's the choice. Practice quiz. Okay. Kind of wanted to talk about this dissolution process. Remember when we talked about this, the dissolving early on with our entropy? We said, what did we have to break? What we had to break was the ionic crystal lattice. This is now going through and talking about quantifying that process. Okay, so you're seeing lots of delta H's and delta S's for individual dissolution processes. Okay, and what they're talking about is what's happening to the kind of force energy as you break them apart. Okay? So you start to break apart those ionic interactions in favor of ion dipole interactions. Okay? And then more, which then takes us, okay, as shown below, calculate the enthalpy change and the entropy change for the reaction using the values in the table. Show your work and include units. Yeah, let's just start with that. So how do we go about doing that? How do you calculate enthalpy and entropy changes? Sum of the number of products minus the sum n of our reactants. Are we actually working through this all the way together? Is that the goal? Yeah? Okay. So if we're going to look at our enthalpy change, delta H, just using our formula, we want to make sure that we tie things appropriately. Our COCl2 is a product, so we're going to start with that. I have negative 217.4. It doesn't look like she's tricky enough to mess with giving you unbalanced questions. I personally, if I had the option, would make sure I had a color change on that, and I would drop in parentheses to ensure that I don't drop that minus sign. Minus the N for my reactants are also all going to be 110.5 kilojoules per mole. I'm going to fix that mole in a second. And then the Cl2 is going to be 0. Why is it 0? This is the enthalpy change of formation from the standard states. Cl2 gas is the standard state. So the change in enthalpy is going to be 0 for that, okay, kind of by definition. Okay, note the parentheses on this. Note the moles. What's going to happen to those moles? Okay. Technically, we can't do this math because the moles are still there. What did we forget? The coefficient is in moles, so officially this would be 1 mole of COCl2. This one is 1 mole, I already forgot what that one was, CO. Whoops, and I dropped the minus sign there, didn't I? And this last one is 1 mole of Cl2, which then means the moles cancel, and now we could deal with our math. I would do everything in the blue calculation first, which was kind of a bit silly, but 217.4 kilojoules. This is going to come out as a plus 110.5 kilojoules. What's the sign on my delta H? negative. I would make sure that negative is emphasized for my sake. 217 minus 110, 100 and, thank you, 106.9 kilojoules is our enthalpy. We good? Okay. I might need that information later. So my delta H at negative 106.9 kilojoules. Now what do I go through and do? I do it again for the entropy value. My delta S. Okay, this time I will go ahead and actually include that 1 mole COCl2 products. 284 joules per mole times Kelvin. Again, I would want to show that minus sign for my own sake. We've got 1 mole of our carbon monoxide times 197.7 joules per mole times Kelvin plus 1 mole Cl2. Why do I have a delta S for the Cl2 when I didn't have a delta H? I think I said that question out loud. Why is there a delta S value for a chlorine but not a delta H? What was delta S a measure of? Entropy, or our S is a measure of entropy. So it's how much our things are actually moving, right? Is the chlorine gas going to move? Yes. So it is inherently going to have some entropy associated with it. Okay? It's not a zero set that we did with the enthalpies. Okay? Our units take care of the moles, so we don't have to stress about those. Numerically, I've got, 284 joules per mole minus
190 over the
Wait, I thought you said they took care of the moles.
by using the N.
Oh.
That's what brings in the moles so that our mole units can cancel, so that we don't have to stress about those. Someone did that math for me in blue. 197.7 plus 223. 418. 17. You just like to watch me squirm doing math? Yes. Is everybody laughing like, yeah? 14.8?
420.8.
Joules per Kelvin. I can now go through and do my calculation, and I'm going to end up with a negative value. Someone give me, say,
136.8.
and then I believe you said something else. Oh, I think I see what you're complaining about. That says mole.
Oh,
Is that what you're complaining?
I was just confused.
Yep. Nope, you saw it. So we get a negative value. .8 joule per Kelvin. The delta H, if you knew the reaction, you could think about exo or endothermic. I don't see any clues. In fact, they're actually asking an explicit statement, is it exo or endothermic? Okay, so they're not telling us that information, so we can't fact check that one. If we're seeing a negative delta H, what is our reaction? Exothermic. Okay, if we're getting a negative delta S, does that make sense? Should we be decreasing our entropy for this reaction? We start with 2 different species in the gas state, and we end with 1 in the gas state. So we're going from 2 to 1. That is a decrease in our entropy, so that does actually check out as being negative. Okay? So we do at least have an internal check on the entropy. We don't have an internal check on our delta H.
Okay.
Does that make sense? Okay, does the entropy of the reaction increase or decrease? Decrease, we get that check. Make sense?
Yeah.
So now we can bring in the next question. Calculate delta G at 600 K, including units. Will the reaction be spontaneous at this temperature? All right, how do we calculate the delta G? Cool. If that's a pause and you're like, I don't know how to calculate that, we now have an equation that we need to write down on our cheat sheet. Delta G equals, cool. We can now go through and start plugging in our numbers for this. Okay. I immediately, believe it or not, am hyper focused on that spontaneous part, right, without actually calculating the delta G. So I would cheat, if you will, and see if I could come up with what that response would be. And unfortunately, what I'm going to find is that it's going to be temperature dependent. The larger the temperature, the less spontaneous the reaction is. Okay, so there is a temperature dependence here. It's not going to be an absolute. Does that make sense? Okay, I would do all that math. What should you do? And in math, it's not math. You're just dealing with signs. I do all the signs. What should you do? Well, you'll need to do the math, but what else? Because we want to be able to put a check in place to verify what our system could potentially be. Look at your quadrants. You've got the quadrants on your note sheet, right? Look at the quadrants and see if it has a negative delta H and a negative delta S. What should that mean? You should be encountering a temperature dependence. Okay? If I was going to ballpark it, I'm saying 600 Kelvin. That seems pretty hot to me. I would start to lean towards this being non-spontaneous at this temperature. Just ballparking. That doesn't mean I'm right. What would I need to go through and do? I would actually need to plug in my values. My delta H was negative 106.9 kilojoules. We do have this note here saying very specifically to include units, which means if you're going to go through and run this calculation, you should probably go through and show those units. Okay, so our kilojoules there, we've got, for the record, just so you all know, I am bouncing back and forth on my screen to see the formula because I, believe it or not, don't hold it in my head. I hold it in my head long enough to write it down, and that's about it. The delta S was negative 136.8 joules per Kelvin because it's a test and I'm rushing, I panic, and I go through and I run my calculation and I get the wrong answer. But if I had time, which generally speaking it appears that most of you do have time since you've written out the units, you would hopefully be able to go back and recognize that we're going to have a unit mismatch, and you would need to fix that unit mismatch. Okay, how do you want to fix that unit mismatch?
You just put it to kilojoules.
Convert to kilojoules. How do you convert it to kilojoules?
Yeah, divide.
To get us into our kilojoules. The Kelvin units will cancel. I then go through and run my calculation. 106.9 kilojoules minus, I'm going to make that a plus right now because I've got the minus sign that now made it look like an equals. I've got that minus sign in there. Together, those are both going to make a plus. 600 times 0.136. 60 something.
Wait. 368, 82.08.
82.08 kilojoules. Do the math, and what do I get? Negative 28.
24.82.
Show off. It's fair. You can show off. Negative 24.82. When I went through and ran the calculation, spitballing into numbers, I was saying it was going to be a positive value. Okay, right? 600 Kelvin seems hot to me. Shouldn't that cause that shift? I would look at that number and be like, it's not too far off. Okay, we're probably pretty close to that transition point. Maybe there's another question that asks when we transition. Does that make sense? Questions about anything that's written there? Oh, we should probably actually answer the question.
Will the reaction be spontaneous?
Will the reaction be spontaneous at this point? And if you're like, I don't know, look at your flippin' quadrants. Okay? Make sure that that is identified on your cheat sheet so you don't have to sit there and spin thinking about it. You can immediately reflex to it. If you have a negative delta G, what does that mean? That is now a spontaneous reaction. Make sense?
Yeah.
Okay. I don't know if I'm going to need that number. I'm a little nervous erasing it. Negative, what was it, 24.8?
Yeah, 18 kilojoules.
I'd be surprised if I need it, but did you have the quadrants written down on your cheat sheet yet?
I'm starting to do
A little bit of shade. Right? Because if you have your quadrants written down, what do you have? Is the reagent product favored or reactant favored at equilibrium at this temperature? You would know that because if you have a negative delta G, that means your K is delta G less than 1. K is going to be, not less than 1, less than 0. That means your K is greater than 1, which means product favored. Okay. You also have an internal check because we know our K is supposed to be greater than 1. Why is that going to be potentially useful? How do we calculate K? See, I did need the delta G. KEQ equals E to the negative
Yeah.
delta G over RT, which equals E to the 24.82. This was in, we had that in kilojoules. Oh, that says kilojoules,
And then
which
just
means when I deal with that R and divide by the R, I need to make that into kilojoules.
Mhm.
I think I did that one right in my head. R, does this one complain about units? It's not saying anything about units. Times our temperature. What was our temperature?
600.
600 Kelvin. I'm dealing with this complex equation. The odds that I enter this into the calculator incorrectly are actually very, very high, for me personally at least. So I'm glad I've got half of the question already answered. Make sense?
Mhm.
Is there a question there? No? That's fine.
Mhm.
Did anybody get that E value? Or sorry, that K value? Or are you just trusting it? You're just trusting it. Oops. 152? Okay. We're getting a KEQ of 152. What should the units be on that? It was a very rude question. We've dodged that question, or not dodged. We've never actually explicitly stated it. There are no units associated with K, and we haven't provided a good reason for it, so don't stress about them. Okay? If you go through and look at the solve that you went through and did here, your kilojoules cancel, your temperature cancels. You've got no units when you go through and run that calculation. If you're curious about why there's no units, you can talk to me after class. Because you said you wanted this. Let's see. We have one more part. Yep, one more part. How would you change the temperature if you wanted to increase the concentration of COCl2 at equilibrium? Explain your answer. So, what is COCl2?
Your products.
Okay, I want my products to go up.
So we do. So it's
Okay, so we could say, oh, we could increase the reactants. If you increase the reactants, that's going to cause the products to go up.
Yeah.
Okay, that's fantastic. Does that answer the question?
No.
No, because what does the what does the question say?
Temperature.
Temperature. Okay, so a couple approaches that you could go through and do. I would immediately go through and leverage the information that we just talked about. This is a negative delta H. A negative delta H means when we go back up to the equation, where should I put the heat term? On the product side. Heat is being released. How do I change the temperature if I want my products to go up? Remove that product so that the reaction shifts to produce more of it. I want to decrease the temperature. Okay. How else could I go through and answer it? The quadrant. That quadrant information allows you to lock into place a lot of this information. One of the problems with using the quadrant, and I know we're over time, is that it does ask you to explain your answer. So you've got to be a little bit more careful about being over-reliant on the quadrant because you still have to go through and explain. You could go through and use Gibbs. You can use any of those equations and you could talk about what's happening in the individual reactions, energy diagrams and all that kind of fun stuff. Okay, that's going back and doing all the stuff that we went through when we talked through that particular section. Kind of, sort of?
Yes.